The Amazon River, recognized due to its large extent of 6,400 kilometers, stretching from the headwater of the Ucayali-Apurimac River in southern Peru to the northeastern coast of Brazil, where it discharges into the North Atlantic Ocean. It is based on this freshwater discharge of the river into the seawater of the North Atlantic that the Amazon is recognized as an estuary. The Amazon River discharges approximately 1.93 times 10 to the 5 meters cubed per second annually onto the North Brazilian shelf, making it one of the world's largest rivers of freshwater discharge. Now, what we're looking at to my right is the freshwater plume that's expelled from the Amazon River. This is recognized as a mixed discharge between the Amazon River and the Atlantic Ocean, covering the continental shelf between 1 degree south and 5 degrees north. The water expelled from the Amazon moves offshore and northwestward along the Brazilian coast. The offshore plume has also been traced to move northwestward into the Caribbean Sea and eastward into the North Atlantic. And according to hydrographic surveys, the Amazon plume is about 3 to 10 meters thick over the shelf and between 80 to 200 kilometers wide. Now, the reason we even care to talk about the Amazon River is that it contributes to over 15% of the world's annual river input into the ocean. And with this discharge, there is an associated expulsion of nutrients, organic materials into the Atlantic, which would otherwise be an oligotrophic environment. Through this presentation, the dynamics of the Amazon plume will be discussed, as well as the 4 offshore factors which the Amazon River influences. These include the sea surface salinity, the sea surface temperature, the emergence of phytoplankton, and turbidity currents. As was briefly mentioned, the Amazon River extends northwestwards parallel to the continent, influencing North Brazil and French Guiana. The dispersion of the Amazon plume begins around March to April, with the surface area of the plume at its maximum in June and July. During the later seasonal peaks, the Amazon plume also enters the Caribbean Sea through the Lesser Antilles Islands. Towards July and August, the Amazon plume will flow around a retroflexion of the North Brazil current between 5 to 10 degrees north. Now, the NBC is a warm current along the western boundary that carries the warm water from the South Atlantic northwest along the Brazilian coast towards the northern hemisphere. And once the Amazon plume flows around the NBC retroflexion, it travels eastwards into the north equatorial countercurrent. NECC is driven by the trade winds in the Atlantic and lies approximately between 3 to 10 degrees north. Finally, between February to May, there is a weakening in the countercurrent and retroflexion, and the Amazon River continues its northwestward flow back to the Caribbean Sea, which is up there. A portion of the Amazon water may also follow a different path during July to August, where it moves eastwards towards Africa through the Guinea Current. So, as I mentioned, I'm going to be introducing the offshore influences of the Amazon River. Now, the first influence I want to address is the sea surface salinity. So, to my left, there is a graph which displays the sea surface salinity changes over the course of a few months. So, it's very clear that the Amazon plume, which is discharged from the continent, is of a different color than the adjacent waters. It is actually of a lower salinity than the North Atlantic, and this is attributed to the fact that it's fresh water being mixed with the seawater. Now, sea surface salinity in the oceans can be influenced by either evaporation-precipitation balance and or advection and mixing. The sea surface salinity is determined by a freshwater balance, in which precipitation and river discharge contribute to the freshwater and evaporative process result in salinity increases. Generally, though, river discharge is not a significant contribution to the freshwater balance, but in the Amazon, the discharge is twice the evaporation minus precipitation balance over the 0 to 10 degrees north and 70 to 20 degrees west. Therefore, it is important to understand how the Amazon influences the salinity values in the western tropical Atlantic. Between 5 to 10 degrees north, the Atlantic Ocean has relatively lower values, around 34 to 35 PSU, which are the ones over here. It has been demonstrated that the lowered salinity values, particularly along the western tropical Atlantic, are influenced by the Amazon River. When the Amazon River is discharged into the Atlantic, it can be carried eastward by the north equatorial countercurrent, based on seasonal variability. This eastward migration of the discharge by the north equatorial countercurrent results in the formation of a zonal belt with salinity values of less than 36 psu that extend from South America to Africa during June to December. Furthermore, the Amazon River also contributes to the seasonal sea surface variability of the Caribbean Sea. Most of the discharge travels northwestwards. Now, the second factor I want to address in the influences of the Amazon River in the North Atlantic are the changes in the sea surface temperature in response to the discharge from the Amazon. So this animation is showing you variation in temperature across the Atlantic from the discharged plume. And we can see that the water discharge from the Amazon River has been shown to produce a halocline within the first 3 to 30 meters of the surface water. These stratifications lead to the formation of a barrier layer recognized as the Atlantic Barrier Layer. It has a shallow freshwater cap on top of a deep isothermal pool, which promotes the capture of solar radiation in the surface layers, resulting in higher sea surface temperatures. This is of relevance to note because if sea surface temperatures are increased, then the conditions become more favorable for hurricane intensifications, which requires sea surface temperatures of at least 26.5 degrees. Now, the third factor that I want to address in relation to the offshore influences of the Amazon are how it affects the biodiversity once it's discharged into the North Atlantic. So I'm going to discuss this graph along the way. Due to the extent of the Amazon River, it flows through a very large area of land. The river makes its way through the mouth of the estuary. It manages to go through very densely forested areas and accumulate sediments, nutrients, and particulates. As a result, when the river is discharged into the Atlantic, the Amazon River plume has a higher biomass of phytoplankton than the surrounding water. Now, the phytoplankton communities were observed to thrive as far as 12 degrees north and could be categorized into 3 groups along the Amazon River. And these are known as the estuarian type, the mesohaline type, and the oceanic type. And the estuarian type are the ones that dwell closer to the estuary discharge point, whereas the oceanic ones are the ones that are further in this area. Now, the estuarian type include the diatoms, the cryophytes, which are directly upstream of the plume. These are phytoplankton which would be more closely resembling those found within the Amazon River. Further into the northwestern area of the plume, there are mesohaline type, which are organisms such as the diatom diazotroph associations, which strive in more nutrient-starved and higher salinity environments. Finally, the oceanic type include the Trichodesmium and the Psychococcus, which are found outside the extent of the plume and can survive in oligotrophic waters. Without the existence of the Amazon River, most of the organisms in the western tropical Atlantic will be like the latter, oligotrophic organisms. Now, the final offshore influence of the Amazon River that I'm going to be discussing are the turbidity currents. Turbidity is the measure of sediment and other particles in a body of water. When turbidity increases, it becomes denser than the seawater into which it is flowing. These turbidity currents enter the ocean and travel below the surface, flowing as underwater rivers to create these submarine channels over time. These submarine rivers appear similar to those observed on land, where smaller rivers known as tributaries can be observed feeding into larger ones. The velocity of these currents is so great that they can carve out valleys in the seafloor, which is what we are looking at to my left. These channels are bounded by levee ridges of sediment deposited along a river by overflowing water, which are created naturally from the spill of sediment down the channel. What you're looking at now is an analog model of a turbidity current. In real life, these flows have an average velocity of 2 to 4 meters per second in the upper fan and decrease to 0.5 to 1 meter per second in the lower fan, traveling over 800 kilometers past the shelf edge. These flows consist of approximately 95% silt, and due to the low settling velocity, the load dominated by the silt may be transported for long periods of time, eventually ending up in the abyssal plain of the oceans. Observing these turbidity currents expelled from the Amazon is important because they have an impact on biodiversity. Some species experience rapid growth when exposed to these conditions, while other species count decrease. Furthermore, the turbidity flows carry nutrients and oxygen, allowing life to thrive in the ocean's abyssal plains, comparative to the deserts of the land. In conclusion, you may be lounging on a beach on Ilha de Maraca, just north of the Amazon River, and never suspect at all any of the underwater occurrences that are happening. These occurrences, however, are important because they can influence the underwater biodiversity, the hurricane occurrences, and even alter oceanic properties. Over the course of this discussion, 4 offshore influences were discussed. These are the sea surface salinities, the sea surface temperatures, the phytoplankton communities, and the turbidity currents. However, to date, less than 5% of the ocean has been explored according to the National Oceanic and Atmospheric Administration. We must therefore continue discovering and questioning the processes which occur in the ocean because they are the drivers of our climate and represent 3/4 of our planet. Thank you.